Welcome back to the deep dive. Today we're looking at something pretty specific, the challenge of sending professional audio over genuinely massive distances.
Yeah, we're talking stadiums, huge broadcast events, that kind of thing.
Exactly. And we're focusing on one piece of gear built for exactly that. The Thor Broadcast F-8A-XLR-PHP-TXRX.
That name is a mouthful.
It is, but it's actually, a roadmap for what it does. F8A is fiber, 8-channel analog. But the PHP part, that's crucial.
Phantom power.
Right. So our mission is to unpack how the system can reliably send 8 channels of balanced XLR audio,
Including that essential 48-volt phantom power for high-end mics.
including that over 20 kilometers on just a single strand of fiber. I mean, that's a huge technical challenge.
It is. And what's interesting is that this wasn't just, an adapter. It was engineered from the ground up for total consistency and stability. It's designed to be completely invisible in the most demanding environments.
Okay, so let's get into the tech, the underlying intelligence. To reconstruct a signal perfectly after a 20-kilometer trip, you can't be using simple processing.
No way.
The docs point to FPGA, digital coding, and clock recovery technology. Why is an FPGA, a field programmable gate array, so critical here? Why not a cheaper off-the-shelf chip?
It all comes down to timing stability. The number one enemy of digital audio over distance is timing error, or jitter.
Right.
So the FPGA's dedicated power, combined with that advanced clock recovery, it just ensures that when the signal arrives, the timing is perfect. It completely eliminates the jitter that degrades audio quality.
That makes sense for fidelity. But then there's the logistics part. The device uses something called CWDM. For the sound engineer on location, what's the real-world benefit there?
This is the big win. CWDM coarse wavelength division multiplexing is what lets you cram multiple signals onto that one fiber strand.
So not just the audio.
Exactly. Your 8 audio channels, controlled data, maybe even a network feed, all on one fiber. It just dramatically cuts down on cabling, on complexity, on cost. It makes the whole setup so much more practical.
And they've clearly focused on making the signal transparent. There's a mention of a noise reduction system with simulated squelch. What does that mean in practice for the listener?
It means you don't get that distracting little crackle or pop when a mic powers on or a signal cuts out. It's a subtle thing, but it simulates that squelch feature to mute any sudden, unpleasant audio artifacts. It's what makes the transitions truly clean.
All that engineering has to lead to some impressive numbers. What are the metrics that define this as truly broadcast grade?
Oh, the signal integrity is astounding. The signal-to-noise ratio, the SNR, is 100 dB.
Which means the background is basically silent.
Virtually silent, no hiss, no electronic noise, and that's paired with a dynamic bandwidth of 101 dB. This is all achieved with really high-res 24-bit sampling at 192 kHz.
And what about distortion?
The total harmonic distortion is a spectacular 90 dB. That tells you almost no unwanted artifacts are being added to your signal.
So the audio is pristine, but for these big operations, durability is just as important. What did the sources say about stability in, harsh environments?
The stability features are critical, yeah. The audio interface itself has level 3 lightning protection, which is serious. And there's a built-in high-pass filter to eliminate DC offset, which guarantees stable operation across a huge temperature range. We're talking -20 all the way up to 70 Celsius.
And it's all designed to be simple, plug and play, sold as a pair, and you can stick it on a desktop or mount it in a 4U rack.
Right. It's meant to just work.
So what this all means for you is that this system really is the cutting edge. It's not just about covering 20 kilometers. It's about keeping near perfect 100 dB SNR audio quality over that distance.
And using that elegant fiber tech like CWDM and dedicated clock recovery to make sure the signal just doesn't degrade. Which brings up an important final question for you, the audio professional, to think about. The device has this huge dynamic range and hits that 90 dB distortion level. But its maximum input level is specified at greater than or equal to 9.5 dB. So in a complex live event where you have unexpected volume spikes, what kind of signal headroom do you have to manage to make sure you actually maintain that incredibly low distortion when the signal peaks? What does that tell you about the future demands on our professional infrastructure?